Carrier injection and selective contact. When we apply a bias to a device, it can inject electrons and transport electrons. But for this to happen, the contact must inject electrons. So it would be more difficult, for example, if there is some insulating layers, so there would be more difficult to inject electrons. And it would be difficult as well if there is not a good electronic match from the energy level of the contact to the energy level of the semiconductor. So if this barrier is about, say, 0.3 electron volts, then it's difficult to inject electrons. Now for holes, it is the other way around. We are going to inject holes from some initial barrier for holes. They're going to then move in the electrical field. And the efficiency of injection then depends on the energy step. So we can see a very large efficiency if there is a good match of the energy levels, and decreasing efficiency when the barrier goes up to 1 electron volt. So then what happens is that we have a device and we have some regimes of transport. As we apply the bias here, we can get injection and transport. And then there is some resistance for transport. This can be ohmic transport. At higher bias, it can go into space charge limited current, for example. When the initial carrier density is exhausted, you need to sustain more charge to increase the current. But there is also, this is the transport resistance, and there is also an interfacial charge transfer resistance at the contact. So if the contact resistance is large, then the device will be dominated by injection. But if the contact resistance is much less than the transport resistance, the device will be controlled by the transport, like in this situation, in which the injection current that the device can sustain is much less than the transport current. So if the contact has a constant resistance, then it's called ohmic contact. And the resistance has to be smaller than the resistances in the rest of the device, for example, for transport. So then we can check this quantity because a transport resistance in general must be proportional to the thickness. So if the total transport resistance is proportional to the thickness, then we are in transport limited regime. Otherwise, if the device resistance is independent of the thickness, then it will be controlled by injection. And this we need to check experimentally. Therefore, a central condition is the match of energy levels, because the transport of electrons occurs in the conduction band, so we need here a good alignment of the energy levels of the contact and the semiconductor material in order to inject or extract electrons. And the same thing happens to the whole transport level, that we need here a good energy match, so that we will have materials with a low work function for good contact to electrons, and materials for a larger work function for a good contact to holes. By changing the contact from a low work function material to a high work function material, we can make the devices primordially conducting holes or conducting electrons, depending on the species that are injected and extracted. Here an example of LQ3 that shows the alignment with different metals that can operate at contacts. But we have to remember that when the material is applied to the semiconductor, there can be formed a dipole layer modifying the position. So that to the right, we see that calcium is around here, but then we apply it to the right and we have this value. It has changed significantly. We can see also that calcium and magnesium, they have the same energy level here. And this is because the contact don't depend on the work function, and this is called the pinning of the Fermi level. Here is an example of aluminium as contact. And then it is deposited LQ3. And we can see by the position of the secondary cutoff that there is a displacement of 1 electron volt. So there is formed a 1 electron volt dipole here. And then this is the position of the conduction band and valence band, or LUMO and HOMO of the LQ3. And there is not such a good match because there's 0.5 electron volts here. In this case, it is often used an intermediate layer of lithium fluoride, because lithium fluoride makes a deeper dipole, which is 1.6 electron volts. This is going to come deeper. And then we have a much better match of the aluminum energy levels and the LUMO of the LQ3, as you can see represented here. Now we move to the structure of a diode. And this is basically a device that will inject electrons in one side and holes in the other side. To form a diode structure, we need that the contacts are selective to only one carrier. Therefore, we need an electron contact that will extract or inject electrons, but will not extract or inject holes. And at the other side, it's the other way around. Here we will need injection or extraction of holes, but blocking of the electrons. Therefore, when we bias the device, electrons and holes are going to be injected at the respective selective contacts. The match of energy level is an essential resource to make a selective contact. In this case, we are having a very good match of the contact to the whole transport level, but here The electrons cannot be injected to the contact because this is in the middle of the gap of the contact. Therefore, this is going to be a good selective contact for holes, and the other way around is to obtain a material that will exchange electrons but not inject holes to these materials like TiO2 in a perovskite solar cell. Another way which we apply to the semiconductor electrolyte interface is to have a kinetic selectivity of the interfacial reactions. Now this redox level is close to the hole transport level, so it will be better accepting holes than not electrons. Therefore, this is a good selective contact for holes at the semiconductor electrolyte interface. These are examples of injection of electrons to the oxidized states of the electrolyte or injection of holes to the reduced states in the electrolyte. And we can see that we can have injection and transport of electrons by a reduced species in solution, and injection and then transport on the electrical field of holes from oxidized species in solution.